Hello children, nice meeting you again from the school bio lab. Today we are going to start with chapter 4, Refraction of Light. Okay, so far the first 3 chapters they were all related to work, energy part. Okay, then the 7th chapter we did, that is sound. Now chapter 4, 5 and 6 are related to light, Okay, so one is refraction of light through plane surface, then you have refraction of light through spherical surface and spectrum. So we are starting with a totally different topic now, light. Okay, now this chapter has 4 subparts. Okay, A, B, C and D. 4 subparts are there, quite a lengthy chapter. Yeah, and regarding the syllabus reduction, only one portion has been cut. One small topic has been cut from this. Turn to page 70. Okay, coming to syllabus, can you see scope of syllabus in the first paragraph? Okay, there are 2 scopes. The first one, so in that, 5th line, if you see 5th line, there is one thing called multiple images in thick glass plate or mirror. Okay, only that is cut. You can just strike it off. Multiple images in thick glass plate or mirror. You can do with a pencil also. So only that portion is cut. The rest all we have to do. Okay. Now, we'll start with, first of all, understanding what is refraction. Okay. So last year you studied reflection quite a lot. This year we are going to see about another phenomena called refraction. Okay. First of all, what is refraction? The phenomena of bending of light when it travels from one optical medium to another optical medium is called refraction. In 8th standard you had the definition. Okay. So simply it is bending of light when light travels from one medium to another. Simple example. Now suppose light was traveling here in air. Okay. Now there is a glass piece here and light is entering into the glass. So what will happen is light cannot go in the straight path. Okay. The reason we'll see later. So what it will do is, instead of going in the straight path, it will bend like this. This phenomena is called refraction. Bending of light when it travels from one optical medium to another optical medium. That is the condition. It should travel from one medium to another medium. Okay. And it will happen exactly at the surface. So sometimes it's a surface phenomena. It's called surface phenomena. Okay. Now the main, I said there should be a change in medium. Now what is so different about these two? They both are transparent, in the sense light can pass through them. But why it is taking a shorter path? To understand that, the simple thing you have to understand is air is a rarer medium. Glass is a denser medium. Now, what do I mean when I say rarer and denser? Density is less, density of air is less, and density of glass is more. It's denser. Okay. So you can, like, here the molecules are much apart. Here the molecules are much closer. That is the meaning of rarer and denser. Now, what happens actually is when the light travels from here and it enters into, it was traveling with a particular velocity, and in air, you know, light travels with a velocity 3 into 10 power 8 meter per second. Now the moment it entered into glass, it will slow down. Why? Because its density is more, so obstruction is going to be more, so the light ray will slow down. But there is one condition, that the frequency of this particular ray, okay, whatever is coming, frequency should be the same even inside glass. Now there are three things if you remember: velocity of light, frequency of light, and then wavelength of light. Okay, velocity might change, wavelength might change, but frequency will not change even when it has entered into another medium. With whatever frequency it came, the same frequency will be here also. So what happens now? If it goes in its usual path, it is going to take time. It is going to take time. Okay, so what it prefers is, it takes a shorter path. It tries to take a shorter path so that it can finish it in less time. Okay, so what it does, that's the reason for bending. Okay, so if I draw a normal here, so this was the original path. It should have gone like this, but it will bend like this and go like this. So if you see the lengthwise, this is shorter than this. So definitely this path, it can finish faster than when it took this path. So that's the reason why it bends and takes the shorter path, so that it can finish it or it in the same time as it took here, because frequency should be same. You know, frequency and time period are related like this. So that is the reason why bending takes place. Okay, so to take a shorter path, mainly because of difference in density, speed of light is different in different medium. Now here I would like to stress another point here. When I say density, I explained you with particles. Here they use a word optical density. Here we'll be using a word called optical density. Air is optically denser than glass. Okay, so you know optics is something to do with light and density, you know. Okay, so this is slightly different from the normal density that we usually refer to. Okay, so always use this word optical density. Okay, now another thing happens is, now for example, instead of the same ray of light, it was originally traveling in glass and it is coming into air. From glass, it is entering into air. Okay. Now, as usual, speed is going to change when it enters into this medium, and its speed is going to increase because this was a denser medium and this is a rarer medium. So, in air, its speed will increase. So, what will happen? It will complete the path very soon. Now, that is also a problem. Here, it will take time to finish, so it has to take a shorter path. Now here, if it goes in the original path, it will finish it faster. So frequency will be different, but time period should be the same as it was for this one. So here it chooses a longer path. Okay, speed is more, but it has to finish in that particular time. So it chooses a longer path instead of shorter path. So this leads me to the conclusion like this. Whenever light travels from rarer to denser, it bends towards the normal. Okay, shorter path basically is towards the normal. Whenever light ray travels from denser to rarer, it bends away from the normal. It bends away from the normal. That means it's a longer path. Hope you have understood. Got some idea about refraction. Okay, children. Now you can open your books. In page 70, come to the topic 4.1, refraction of light. Now in that, there is a first sentence says, partial reflection and refraction at the boundary of two different media. Now actually what happens is, whenever light ray enters a medium, like what we were talking here, actually part of it will be reflected also. Okay, so Not that entire 100% of light will be refracted. It is found that only 95% will be refracted, in the sense going into the other medium. Remaining 5% of light might be reflected back into the same medium. Okay, this is refracted ray and that is reflected ray. Hope you remember reflection means bouncing back into the same medium. Okay, so when refraction takes place, partially reflection also takes place, but in all the explanation we are going to omit it. Okay, we are not going to pay attention to it because this is very less energy is only reflected, mostly it is refracted. But you should know this fact that part of it will be reflected also. Okay, so that is what is they are trying to give in the first part. Okay, partial reflection and refraction at the boundary of the two medium. Okay, now below that there is this term optical density. Okay, can you see some blue lines here? Okay, some blue lines there. Third line, so in the first line says optical density has no relation with density of molecules, means they are totally different. Come to the third line, optical density of a medium depends on speed of light in that medium, whereas density of a medium depends on the distribution of molecules or intermolecular separation. Okay, now come to the next page. You have the definition of refraction. So how do we define refraction? Okay, can you see this in the block? That is defined. Okay, so definition goes like this: the change in the direction of path of light when it passes from one transparent medium to another transparent medium is called refraction. So change in the direction of the path of light. Okay, so instead of going in this direction, it's now going in this direction. Okay, this is also another way of saying refraction. When it passes from one transparent medium to another transparent medium is called refraction. Refraction of light is essentially a surface phenomena. Okay, it is a surface phenomena because it happens at the surface. Now, come to the right hand side. On the right hand side, there are three diagrams. Okay, I hope you are able to see three diagrams. I have named it Rule 1, Rule 2 and Rule 3. Okay, so the Rule 1 is refraction from rarer to denser. When light ray travels from rarer to denser, this case. Okay, so they have not shown the glass and all that, in the sense they have not shown the block. They have just shown the surface of separation because it is a surface phenomena. It's enough if you show the surface. So they have not even shown the exact medium. They just took like this. This is a rarer medium and this is a denser medium. So that is the first rule. Okay, I just take it as Rule 1. Whenever light travels from rarer to denser, the ray bends towards the normal. Bends towards normal. Okay, you can just underline these two words. Okay, in this first point, when a ray of light travels from a rarer medium to denser medium, it bends towards the normal. Now we go to the next rule. Okay, that is when ray of light travels from denser to rarer. Again, you don't have to put a block. You just are going to show a surface of separation. Surface of separation. Okay, for Rule 2, we are just going to take a surface of separation and this is denser and this is rarer. Light is coming from denser medium and going into rarer medium. So this is the original part. It should have gone like this. Okay, I put in a dotted line. The original part I put in a dotted line, but it bends away from the normal. Bends away from normal. Is it clear, children? So, these are the two important rules you have to remember because we'll have a lot of ray diagrams in this and we'll be applying these rules. There's another rule, Rule 3. I just name it this. I'm just naming it for convenience. Okay, in the book it's not there. Case 1, Case 2, Case 3 you can take. Case 1, Case 2 and Case 3. Case 3, suppose if a ray of light is incident along the normal. If it is incident like this, okay, this is a rarer medium and this is a denser medium. Now here and all, it was incident in a oblique manner. There was an angle here. This angle is called angle of incidence and this angle is called angle of refraction. Okay, so in this case, if it is going to be incident perpendicular without bending, without any angle, then this ray will go undeviated. The ray will go undeviated, in the sense no bending will happen. There will not be any bending. It will go in the straight line path. Simply because angle of incidence is 0. Don't say 90. Angle of incidence is angle between the incident ray and normal. So this is the normal, this is the incident ray. So angle of incidence is 0. Angle of refraction will also be 0. Now in this case, if you see, in case 1, angle of refraction will be less than angle of incidence. Okay, because it is bending towards the normal. In this case, angle of refraction, this is angle R and this is angle I. So angle of refraction will be greater than angle of incidence. Is it clear, children? So these are the 3 rules that you have to remember while drawing all the ray diagrams. Okay, so you can underline. So in case 1, you will underline this part. Rarer to denser bends towards the normal. Then come to second point. Denser to rarer bends away from the normal. Okay, and third one, the ray of light is incident normally on the surface. The ray passes undeviated. Normally and undeviated are the important words, and these 3 diagrams. Now in these diagrams, reflected rays are also given. The diagram actually, they have given the reflected ray also, but you need not. Okay, with a pencil please cross. I have put a cross near the reflected rays, so you can just cross it here and here. Okay, because there is a note here which says, in discussing refraction now onwards, the reflected ray from the boundary surface will not be shown, although it is there always. Okay, because we are not going to show it. Okay, children. Now we go to the next topic. So this is like introduction. All that we saw so far is like introduction about refraction, why it happens and how it happens, what are the 3 possible cases and all that. Now we'll go to the next topic. That is laws of refraction. Okay, in the next page, if you see, come to page 72, at the top there is cause of refraction that we have discussed already. I want you to underline the 3rd and the 4th line in that. Please underline 3rd and the 4th line. In that, direction changes because of the change in speed of light when it is going from one medium to another. Please underline that. Direction of direction or path changes because of the change of speed when light travels from one medium to another. Okay, now you can put an arrow mark here and write due to change in optical density. Why does this happen? Due to change in optical density. So this, the heading I would give is, a heading you can just put a tick mark here, cause of refraction. Why does refraction take place? So this is explained here, but these are the first 4 lines are important. Along with that, I want you to write this also, because due to the difference in their optical density. Now we go to the laws of refraction. Okay, these are the portions that we are going to see from now on is very important. Okay, so laws of refraction. If you remember, we had laws of reflection also. The same way we have laws of refraction. Okay, so the first law, there are 2 laws. Okay, first law says incident ray, refracted ray and normal all lie in the same plane. What do you mean by that? When you are performing this experiment, okay, you'll be drawing this ray diagram. So You will get a ray like this. So this is the incident ray, this is the refracted ray, and this is the normal. All of them will lie in a single plane of paper. You know what's a plane? It will have two sides, right? So this can lie in a single plane. It's not single line, it is single plane, same plane. Okay, that's the first law. Same way, if you remember, in laws of reflection also, the first law will say incident ray, reflected ray and normal lie in the same plane. Here it will say incident ray, refracted ray and the normal lie in the same plane. Okay. Now coming to the second law, this has a special name called Snell's law. Okay. This is a person who found this law. So that's why, okay. His full name is Wilbur Snell or something. So they gave the name to the second law as Snell's law. The second law says, okay, this is, I told you this is angle of incidence and this is angle of refraction. Now, sine of angle of incidence, ratio of sine of angle of incidence, okay, up to sine of angle of refraction. You all have studied this trigonometric constant sine, okay. So, sine of angle of incidence upon sine of angle of refraction, or ratio of sine of angle of incidence to sine of angle of refraction is always a constant for a particular pair of media. For a particular pair of media. Okay. Now, you know that depending on I, R will also change. Yeah. Now, what does the rule say? Suppose, imagine this was, when you had this as 30 degree, angle of refraction was 28 degree. Okay. So, when you do, I'm not sure, I'm just taking an example. Okay. So, you would have, suppose you would have got answer as 1.5. Okay. You know the values you have to put and take. Okay. Now, I'm taking another incident ray, the same medium, the same thing, but I'm taking a ray at say 45 degree. Now I'm taking another ray at 45 degree. Now this was the original path, but it went like this, and say this was 38 degree or something. Okay. When it was 45 degree, when angle of incidence was 45, the angle of refraction was 38. So, if I find the ratio of angle of incidence to the corresponding angle of refraction, then also the answer will be 1.5. Okay, so I'm not saying this is 1.5, I'm just taking an example. For a particular pair of media, the ratio of angle of incidence to angle of refraction will always be a constant. If it has to be 1.5, if it is 1.5 here, it will be 1.5 here also. Any angle ray, incident ray you take, correspondingly refracted ray, angle of refraction will change. But if you find the ratio, it will be, okay. So this is the second law, which says sin I by sin R is a constant, and this is called Snell's law. And this constant is called refractive index. So we come to another term called refractive index, that is, okay, and the symbol of refractive index is mu. Okay, it's a Greek alphabet, mu. So mu is equal to sin I by sin R. Yeah. So here the laws of reflection is given. I want you to put a tick mark near that. The first law says incident ray, refracted ray and the normal all lie in the same plane. I want you to underline same plane because it's not line, it's same plane. Okay, then the second law, ratio of sine of angle of incidence to the angle of refraction. Sine of angle of refraction is constant for a given pair of media. Okay, sin I by sin R is constant, and that is mu to 1. So, Greek letter mu, you pronounce it as mu, refractive index. Okay, this leads us to the definition of refractive index. So, I have written define refractive index based on Snell's law, because there is one more definition for refractive index. So I want you to write here, define refractive index based on Snell's law. So same thing, what you have given here, they have given as the second law. Okay, now this part I'll do next. Now come to the second definition. Okay, there's another definition for Snell's law that is based on turn to page 73. Okay, there's another definition for refractive index given here. I name it like this, refractive index based on speed of light. That was the definition of refractive index based on Snell's law. This is the definition based on speed of light. Now, this, the one that we saw so far, sin I by sin R, this formula I can use only when I am doing it practically. When I am doing it practically, in the sense I need to perform the experiment, find the angle of incidence. Okay, as I showed you, like for example, if this is 30 and this comes out to be 28, how do I know all this? We have to perform it practically. You will also be having this experiment. You will also, when you come to school, you will be doing it. So this formula we can use only when you are doing it practically. Now theoretically, if I have to calculate the refractive index, then there is another formula for that. Okay, so that is speed of light in air. So it is the ratio of speed of light in air or vacuum upon speed of light in the medium. Now suppose light is traveling from air into glass. Okay, so speed of light in air upon speed of light in glass gives you the refractive index. Okay, speed of light in air or vacuum upon speed of light in that medium. Okay, it will be different and accordingly the value will be also different. Okay, now there are two reasoning questions. I just finished that. The refractive index of any medium, of a transparent medium, will always be greater than 1. This answer, the refractive index, will always be greater than 1. You will never have an answer less than 1. If you see, there is a table that has given the refractive index of many things. Always it is greater than 1. Minimum is 1, 1 or greater than 1. Why is it so? Okay, it comes from this formula. Now, so refractive index formula is speed of light in air upon speed of light in medium. You know that speed of light in air is the maximum. In air, it travels the fastest. That is 3 into 10 power 8. In all other mediums, it will be less than 3 into 10 power 8. For example, if it was glass, it will be 2 into 10 power 8. The speed of light will be 2 into 10 power 8. So what will happen? 3 upon 2, 1.5. So there when I showed in the board also. So here using this formula, sin 30 by sin 28 also, you might get 1.5. If it was glass, using this formula also, you will get 1.5. So that's why I said this is another formula for finding refractive index. Now the question is, the answer for that question is, because C of air is always greater than the speed of light in any medium, it will always be, mu will be always greater than 1. Okay, so because speed of light in any medium is always less than that of vacuum or air. Okay, vacuum or air. Okay, then there is another possible question in this. What do you mean by the statement refractive index of diamond is 2.41? So in this table, children, I want you to put a tick mark on. You cannot remember all that. This is the refractive index of some common substances you should know. Vacuum and air. Vacuum or air, it is 1. Water 1.33. Ordinary glass, it is 1.5. Diamond 2.4. Okay, so you have to remember this. Now there's another question based on this. What do you mean by the statement? So when I say refractive index of diamond is 2.7, what do you mean by that? What do you mean by this? What information does this give you? So you know that refractive index formula is speed of light in air upon speed of light in the medium. Here medium is diamond. Okay, you can take it as diamond. So this is given as 2.7. So into, I can bring this to the numerator. So into speed of light in diamond will be the speed of light in air. So I can say speed of light in air will be 2.7 times speed of light in diamond. This means if I say refractive index of diamond is 2.7, what information does it give? It immediately gives me this idea that speed of light in air is 2.7 times speed of light in diamond. Now, for another example, if I say refractive index of water is 1.33, what do you mean by this? Same 1.33 will be based on this formula, speed of light in air upon speed of light in water. So you cross multiply it. So speed of light in air is 1.33 times speed of light in water. That is the conclusion. This also comes as a 2-mark question. I want you to write it like this. What do you mean by the statement? The refractive index of diamond is 2.41. Answer will be, it means that light travels in air 2.41 times, sorry, it's not 2.7 children, it was 2.4 times faster than that in diamond. Okay, like this they can ask you giving any of these values. I hope you have understood clearly so far. Thank you children.